School,
All right.
school.
Hello, everybody. This is Grishma from Morgan Stanley here to talk about using Qiskit for financial applications. So thank you so much.
Yeah, it's cool. Yeah, thanks for having me here. Uh, yeah, I hope I'm audible. I am, right? That's okay. Cool. So yeah, I really hope all of you are having a good time at the Qiskit Fall Fest. I hope you're having a nice day. I think it's evening there. Uh, yeah, so as Adrian just said, I am from Morgan Stanley. I have been learning and understanding quantum computing in general for some time now. I also became a Qiskit advocate this year. So, yeah, it's an honor to be doing a workshop on quantum finance for Qiskit Fall Fest. Uh, I really hope that post this workshop, uh, all of you actually have that urge to explore quantum finance even more. So, uh, yeah, I think I can just get started perhaps. I'll share my screen in just a sec. Uh, so, Adrian, it says host disabled participant screen sharing. I think you're on mute. I can't hear you.
Oh, sorry. Can you try now?
Huh, sure, let me just. Cool. Is it visible?
Yep, I can see that. Thank you.
Cool. Yeah, so the agenda for today is basically about covering three use cases. Uh, so, uh, yeah, so we'll be covering three use cases. And of course, quantum finance has many more use cases. So this is just kind of a primer. And of course, after this, you could go on and uh, explore more topics, more use cases. And that's the idea of the workshop. So I'll be covering these three use cases, and whatever I talk about in these use cases could actually be applicable for other use cases as well. So some other use cases being, something like derivative price. So that's something that I won't be particularly talking about here. But then, yeah, like for example, the algorithm that's being used here, the classical approach which is being used here is also applicable there. Uh, Also, I believe that some of you may not be exactly acquainted with finance in general. You may not know the classical approaches that are used in finance. So I feel that since this is about quantum applications, it would help if I give you some idea of the classical approach and then move on to the quantum approach and say how that actually gave a speed up or an advantage. So that's my idea for today. And then, of course, the example, especially for the first use case, the example that I have taken is also from uh, one of the Qiskit, it's inspired from one of the Qiskit tutorials. And at the end, we'll also be talking about the Qiskit finance module, which is a part of the overall Qiskit framework. So it's very seamless and very easy to use the Qiskit finance, which we'll also talk about. So moving on. Hold on. I'll just again screen share just a It's visible, right?
Yeah.
Uh, so moving on, uh, if we so let's start with the first case. So there's something called as Monte Carlo simulations. This is not exactly just useful for finance, but it's actually pretty useful in several areas. And what that essentially means is, so for example, let's say I have a model wherein I have some independent variables and a dependent variable. I construct that model, but there are cases where I may not exactly want just the predictions. I may want something like a worst case value for an outcome, or I may want something like a best case value for an outcome, or I may want some other type of an outcome. I want to have an estimate of that specific type of an outcome of uh, my output, desired output. And so, in such cases, what we essentially do is we kind of either assume or we through the historical data of the independent variables, we would actually have some kind of a distribution for each of them. Uh, the distribution in terms of, say, statistical distribution is what I'm talking about. And so when you uh, want to actually get the output distribution, you just randomly sample from each of those independent variable distributions and apply a model of interest and get a distribution for the output. So yeah, I think this is quite a uh, uh, high level detail that I gave. I can probably give an example. So for example, let's say you want to uh, know the best return of a stock, and now that stock actually is influenced by several factors. So be it how the market is working, uh, be it how the stock return has been in the past, be it how the company of which the stock is performing, etc. So there are several factors which can be demand and supply of the stock, etc. So there are several factors which may be influencing the particular stock. And so what you want is for each of those independent features, you actually construct a distribution and you basically draw random samples from each of those. And now, so the idea of drawing random samples is to basically construct several scenarios. So one scenario will be where the market is doing extremely well. One scenario could be where the market is doing absolutely bad. So you can have several such scenarios, and you would have, for those scenarios, you will have an output value, uh, and you would thus, when you take random samples, you'll have several, maybe, so you can do 1 million to several thousands to millions of simulations, and you can get those many number of scenarios and those many number of output results. And you will have, the more simulations you do, the better distribution you will get for the output. And that's the idea of the Monte Carlo simulations. And in words, this is how one could just mention what it is all about. You have exactly what I just mentioned. You have independent variables, you define a model, you then have probability distributions for each of those uh, independent variables, and then you randomly sample and you have a distribution for your output. Uh, Going on, there are certain things. So, finance is a lot about risk. And so it's key to understand certain metrics, one of them being value at risk and other being something called as expected shortfall. So what we mean by value at risk, it's a simple concept, but it's a very important concept in the risk domain of finance. So for example, the plot you see here, which I have taken from Investopedia, you see that you can actually, so this is about the daily return. So what I'm actually trying to see, what is my risk? The risk is when my returns are actually low. So I'll probably look at the distribution from the left hand corner, and I'll define some kind of a confidence level. So let's say I say that 0.05 is my confidence level. So you see, usually your lower returns is a rare phenomenon. So it will come with a lower probability, but it's again something that can happen, and that's pretty risky for you if you're investing in that stock. So uh, you look at the lower end, and if you see this orange uh, uh, area here, that exactly indicates the amount of risk you have. It's the amount of uh, low return or the loss probably that you will have if you are into the stock. So yeah, the interpretation can differ. Let's say this is about talking. This is when we are talking about gains of a stock, returns of a stock. You could potentially be talking about, in general, in a bank, when we uh, talk about, say, capital adequacy, it usually means that you have a portfolio, and you could be making, so you basically need a certain amount of capital to cover your losses. So you would have a loss distribution instead of a return distribution. And you would actually look at the right hand side, where your loss again is rare, but it could be a significant loss. So the bank would need sufficient amount of capital so that it can cover up those losses. So that's the whole idea of value at risk. Expected shortfall is again similar, just that you don't stick to a single value, but you stick to an average value, or an expected value of all the returns or losses you have at that specific confidence level. So, yeah, mathematically, it would look like the formulas I have given here. But yeah, this is essentially the core idea of the risk measures that we usually have in finance. Uh, Moving on. Yeah, so I'll just take a simpler problem statement. And this is inspired by this tutorial from Qiskit, which is about credit risk analysis. And the problem is that we have K credit instruments in our portfolio, and we would like to find the VAR and the expected shortfall. And why is this a simpler problem is because usually your portfolio could be comprising of several types of instruments. Here I'm only considering the credit instruments. And what I mean by credit instruments is something like uh, for example, your credit card itself, like you bought things from your credit card, but you defaulted in paying back later. So that's kind of a default that at your end. So when you invest in a credit instrument, it also could mean that you are, let's say, uh, giving a loan to someone, and that someone is supposed to return you back with some interest, some cash with interest, but that person fails to do so. So that's a loss for you. So that's basically a default for you, and that's a loss for you. So, given, so if let's say you have these K instruments, and you have an idea of what the loss given default for each of those instruments is. And so if you really look at this problem, you have K instruments, and you can have several possible combinations of default or no default for different uh, instruments. So generally, when someone tries to construct their portfolio, their idea is to have something which is very diverse. You don't want one particular. So, for example, you may not want something which is. You may not want several instruments which are at the loss at the same time. So you would kind of have type of a balance. So yeah, if and if even any of one of you, or if, any I mean if among you there are people who are interested in investments, you will know this. Like you would kind of uh, go into constructing a portfolio where you'll try to make it as diverse as possible, where you would not want to have losses on everything at the same time. Uh, and so, yeah, you would try to ensure that they are not too correlated uh, with each other. But yeah, coming back to the problem statement, yeah, so we have all possible combinations of default or no default. And if you really think about this, and if we, let's say, uh, have to look at this from the Monte Carlo simulations perspective. Uh, what you would be doing is you would be having a, let's say, uh, you so your default, the probability of default here itself is not constant if you really see, because that itself can vary depending on the market situation and several variables. So you will have a distribution for your probability of default, and that in turn depends on several factors. So what we essentially do here is we consider all those factors, the independent variables. We can just consider them to be some kind of a latent variable, and your probability of default is just a function of that latent variable, or you're basically mapping your latent variable to the probability of default for each individual asset. So you have that, and so yeah, this is everything from how you think about it classically. And if we look at the Monte Carlo approach, or this whatever uh, the the written part of this Monte Carlo simulation here, uh, as I just said, you need several simulations to get an appropriate distribution for your output. And that could mean, I just gave simple example of a stock. You could have a portfolio, and you could have several thousands of factors affecting a portfolio. So you could imagine, if I have to randomly draw a sample, and if I have to draw several samples, millions of samples, uh, you can see how huge the possible number of combinations could be. And more the features, the more number of simulations I would have to do. And it's classically a very popular approach and very famous approach, which is used uh, a lot. But then we have quantum approaches which have shown an advantage. And so uh, this particular algorithm here, the quantum amplitude estimation, is one of the uh, most popular ones, which has shown a quadratic speed up over the classical approach of Monte Carlo simulation. So if you think about this problem in terms of, say, in a quantum way, if you have to think about it in a quantum way, essentially if you look at this uh, state that I have written right here, what this essentially means is that so this state one basically means default, state zero means no default, and essentially what I want to find is this probability of default for every asset. And this probability, as I said, depends on the latent variable that we just discussed here. And and since you are having k assets, you would have to kind of consider all of them. So you have like a tensor product of these states here. And also, because it's dependent on the latent variable, you also need to consider the probability of uh, that particular instance of the latent variable existing as well. So you also have this T factor here, where you're actually doing the probability of Zi. Zi is just one instance of that latent variable. So in when we implement this, what we essentially do is we consider a latent variable, And usually you consider the latent variable. So it's a very common practice to consider, to assume a standard normal distribution for your latent variable. So because it's always very intuitive and easy for us to imagine a standard normal variable. What a standard normal variable is exactly a plot like this. But this is not exactly a standard normal variable. Usually in a standard normal variable, you have the peak occurring at a zero value. So usually that's like a standard distribution that we always consider. And then we further bring in complexities to it by mapping that distribution to other non-intuitive and random distributions. So when we, so yeah, coming back to quantum amplitude estimation, this is what is your initial state. As I just said, one is the default state, zero is the non-default state. You're interested in the probability of default, and your probabilities are dependent on the latent variable that I just talked about. And if you want to, when you want to implement this, if you want to, you can represent your latent variable with, say, if you, let's say you need, let's say you want to represent it with n qubits, which means you are considering 2 raised to n possible values of your latent variable. And so yeah, it's exactly like in case of Monte Carlo, where you were randomly drawing samples for your independent variable. Here, it you can intuitively think of it as having 2 raised to n draws of your latent variable and your distribution of your independent variables accordingly. So the quantum amplitude estimation, uh, the original version of it. So there are several variants of it, and I'll just be covering the one which just came out in the beginning, the original version of it. That's basically a combination of Grover's algorithm, or basically a quantum amplification algorithm, and a quantum phase estimation algorithm. So uh, Grover's algorithm is a very, very interesting algorithm. I personally find it very fascinating how someone could think of an approach like that. It's generally used for searching from an unstructured database. So if you think from this problem statement, you are essentially looking for that single var value at risk value, right? Or you're looking for an expected shortfall. So you're essentially among a bunch of states, you are looking for that one value. And in this case, you're looking for example, in the problem statement we considered, you're looking for that one uh, combination of defaults and non-defaults, which is most probably the default scenario for you. So you may not, so one may think that you can have the worst cases when you have default in everything. But as I said, since your portfolio, you would be designing in such a way that you don't incur losses in everything, you would probably have something like a combination of defaults and non-defaults, which could be really bad for you as a investor or as someone who's just generally investing into uh, financial derivatives or instruments. So yeah, so the idea of Grover's algorithm is to identify that bunch of states or that single state. So bunch of states for, say, something where you want to find the expected shortfall or an average of losses. And value at risk is like the single loss combination that you would want. And yeah, so in Grover's algorithm, essentially, you have, uh, if you look at this, it's basically you have this winning state W here. You consider a superposition of states, and essentially, and then you consider a state which is basically orthogonal. And this is a very high level picture of it. If you are not aware of Grover's algorithm, and if you would want to learn that more, I would highly recommend you going through the Qiskit textbook where it's explained beautifully. Uh, in fact, this picture is also taken from the Qiskit textbook because I felt that it's quite explanatory. So you take the winning state, you take the orthogonal state, and essentially you perform two reflections. One about the superposition state, which lands you here, and I haven't added another. There should have been another plot diagram here, which I missed perhaps. But you also have, so once you do a reflection around this state, this orthogonal state to W, this S dash, you basically your S being reflected is reflected here. And then you reflect your this state, the state which is represented in violet here, about this particular uh, the superposition state that you get here, and your state eventually would land up here somewhere closer to the winning state, and you repeat this process of the reflection about the superposition state several times so that it gets closer and closer to the winning state. Again, I mean, if this is very high level, you can always go through the Qiskit textbook. But I think the plot to the right uh, is probably even more intuitive. So, for example, the blue is basically the winning state. You kind of reflect it about the superposition state that you had, and that goes down. That is basically reflected. So it comes down, and then you again reflect it about. So once you do a reflection, your overall superposition, because now it's a superposition of again of every state, but your amplitudes would kind of come downwards, and that's why this hashed line is what you see here. And then you again reflect it about that hashed line, and your uh, state would actually get amplified above, and that's what would be the state. If you measure it, that's the state that you'll get with the max probability. So yeah, Qiskit textbook is the resource for learning more about uh, Grover's algorithm. Again, the original paper actually has quantum phase estimation. The newer versions of quantum amplitude estimation, they have actually come with variants where they don't include quantum phase estimation because it's actually a very expensive algorithm. And given that we have uh, noisy backends right now, noisy quantum computers right now, it's not uh, viable to use some algorithm of that kind. So there are several variants of it, but the original variant does include quantum phase estimation. So yeah, this slide looks pretty packed, and this yeah, I won't go into the details of quantum phase estimation, but the key things to note about quantum phase estimation is one thing, which is a very, very important concept known as a phase kickback, which comes in uh, several algorithms. So in fact, even in the Grover's algorithm, when we actually want to perform a reflection, or when we want to when we want to bring in a negative phase to a given state, we essentially have like an ancilla qubit, which would typically be in a minus state. And when we perform an X gate on it, it would essentially have a negative phase, which would get kicked back to the relevant winning state. So that's the core idea of a phase kickback. And once you have, uh, so then so yeah, this is exactly what phase kickback is through these diagrams. If you once you have another thing is important thing in every algorithm is of course measurements. So one the idea of estimating a phase is basically to uh, measure the state and get you after measuring the state is when you can actually get an estimate of your phase. So if you look at what I have, these two uh, snapshots, you see, I'm actually taking an X state, I'm applying a phase gate to it. It's getting that phase which I want, and I'm measuring it in the X basis. So when I'm measuring P plus, basically means that I'm measuring it in the X basis, and I'm getting the value as 1 plus cos phi by 2. So then once you have that measurement, you can always get an approximate value for your phase. Uh, so yeah, and similarly, you have this as well. You can do this with the plus I eigen state of the Y poly uh, gate, and you'll have, if you measure it in the X spaces, you will have something like 1 minus sine phi by 2. So yeah, essentially the idea of quantum phase estimation is phase kickback. A few things to note is phase kickback and measurements. And yeah, there are other details here. So for example, uh, this exactly this small algorithm that I have just mentioned here and even here essentially are talking about that. You apply a phase gate, and then once you measure, you can actually learn your phases. And an important thing to note here, which I won't go into details, is about uh, binary fractions. So binary fractions are pretty uh, cool. I think you'll definitely find resources to read about that online. So essentially, you have a phase, you want to convert that into, and your phases could be decimals. So when you want to convert it into a binary fraction, which means a fraction in terms of only ones and zeros, uh, you have a nice standard algorithm to do that. So you can always have that. And so when you actually do the measurements, you will actually get phases in terms of these decimals, B1s and B2s and B1. So why you need these binary fractions is essentially because uh, your qubits are in, like, you will basically be measuring in terms of ones and zeros. I mean, yeah, this is a very high level overview. Again, you can go through the Qiskit textbook for it. Uh, I remember in the Qiskit Summer School 2020, there were there were certain lectures based specifically on the quantum Fourier transform and quantum phase estimation, which are very interesting, and you can always go through it. Yeah, the second thing which I would so yeah, this was one phase. Yeah, one thing is, so yeah, with coming back, I think since we spoke a lot about these algorithms itself. Essentially, the problem here is to, if you really look at it, we want the right state where we get the combinations of defaults and no defaults. We want the probability of, we want that state, and we also want to estimate the probability of default. So you see where quantum phase estimation is coming in here, right? Because we are not only interested in that state which gives us the worst case default. We are also interested in estimating the probability of default. So that's where the phase estimation comes into picture, because you would want to estimate that amplitude of that particular state. Uh, Coming to the next use case, which is about portfolio optimization. So portfolio optimization is a very, very common problem statement in finance. So it's like any other optimization problem. Essentially, what you want is you want a portfolio wherein your uh, risk. So one thing is that I mean, it's probably very intuitive. The more risk you have, the more possibility of a return you may have. So uh, you may have investors who are risk averse. You may have investors who like to take risk as well. So those who like to take risk definitely have chances of making huge returns, but they are also at the risk of making extreme losses. So when people like us actually want to invest, we would want to get some kind of an optimal portfolio where our risk is not something we'll be scared of when we incur losses. And at the same time, with that risk, our return is quite optimal and maximum. So that's what we essentially want to do here. So our objective, so every optimization problem has an objective which we want to maximize or minimize. So here in this case, we would want to probably maximize our returns, and the constraints we'll have would be based on the risk. So risk typically here, as I initially in some time ago I just said, you would want a portfolio which is kind of diverse. You don't want things to be correlated. You don't want everything to have a loss at the same time. So risk is one way of assessing the risk in your portfolio is essentially taking a covariance between all the assets in your portfolio. And uh, so, yeah, this is, I think, the classical optimization might be familiar to a lot of you. So, you would have an optimization problem, you'll have constraints, and you would want to solve that problem. And you have several classical approaches, and you have uh, even several classical ways of doing it through programming. But if you want to think of this problem in a quantum way, you would essentially want to map your uh, objective to a Hamiltonian. So a Hamiltonian is, in layman terms, it's just some kind of a matrix. And in quantum, so when we talk about quantum systems, we are essentially talking a lot about the energy of the quantum system, the energy states, the eigens, energy, the eigenstates. So energy states are basically the eigenstates, and the corresponding eigenvalues are the uh, energy values of those eigenstates. So we are essentially talking about a quantum system in terms of energies. So your Hamiltonian is essentially uh, representing the energy of your quantum system. So when we in finance, when we so one very popular algorithm that is commonly used in all these. So if you look at this problem, it's essentially a combinatorial problem because you have, let's say, a bunch of asset classes. Sorry, you have a bunch of assets, and you want to kind of figure out which asset to invest in, how much to invest in, uh, and at what point to invest more in, at what point to not invest in. So it's essentially a kind of a complex combinatorial problem, and QAOA is one of the popular approaches that's used here. But QAOA is essentially a specific form of another general algorithm known as a variational quantum eigensolver, which is mainly used in chemistry applications. So, just very briefly going over what VQE is, your quantum systems essentially have discrete energy states. And what you essentially want to find is the when you so if you look at an analog to the classical part, essentially what you want to find is the energy value that corresponds to the ground state, which is analogous to finding, say, the minimum of your objective function in terms of your problem statement. So that's what we do. And what we have in a variational quantum eigensolver is we have something called as a variational circuit, which is often also called as an ansatz. So you have, so it's very similar to, uh, let's say, something like machine learning, where you have, let's say, if you look at, say, a neural network with lots of nodes, and you want to basically find the best possible weights. So essentially, so you can consider your neural network, though your architecture is set, your neural network is basically something like a variational circuit. I mean, it's not a circuit in quantum sense, but it's variational in the sense that your parameters you can keep tweaking your parameters and coming up with the best possible parameters that give you the best possible results. So essentially, you do the same thing here. This is a hybrid algorithm with where you uh, have your circuits as quantum circuits, but your optimizer is essentially a classical optimizer, like any gradient based optimizer or uh, something. Yeah, so any gradient based or even non gradient based classical optimizer. So a QAOA is a very specific form of VQE, and you essentially have QAOA looks has a very specific type of circuit design or ansatz. So you essentially have all Hadamards first, and then you have an alternating uh, uh, problem Hamiltonian and a mixer Hamiltonian. So you have, and you can repeat them. The more you repeat, the more costly or, like since you're running it on a noisy quantum computer, the more errors you may incur. The less you run, the less errors you may have, but your accuracy and precision may be less with less repetitions. And the problem Hamiltonian, which I just talked about, is the Hamiltonian I was talking about, where you map your objective function to a problem Hamiltonian, but you also have something called as a mixer Hamiltonian. And what the idea of a mixer, this wasn't very intuitive to me in the beginning, I would like to confess, but the mixer Hamiltonian is essentially used so that you could get a global maxima or a minima. So a common problem in optimization problems is that you may get stuck in local maximas or minimas. Uh, but so the idea of a mixer Hamiltonian is to kind of avoid that type of a situation where you get stuck in a local maxima or a minima and you hopefully get a global maxima or a no, minimum. So that's exactly the idea of a mixer Hamiltonian. Again, for QAOA, there are I think this YouTube video that I have just linked here, it's the theoretical part of it is explained really well, especially how you map your problem statement to your problem objective function to a problem Hamiltonian. That's explained pretty well in that particular YouTube video. So you can always go through that. You can also go through the Qiskit textbook, and you can also go through tutorials in the Qiskit GitHub, especially in Qiskit optimization and even in Qiskit finance. You can definitely look at the tutorials there. So yeah, that's one. And I think yeah. So yeah, I was wondering if I'll be able to complete it on time. But yeah, one last application is quantum machine learning in finance. So a typical use case is fraud detection. So I mean, you might know in a financial institution, fraud is a big thing, a huge thing. So it's so that's why fraud detection is often solved through machine learning algorithms. Typically, you use things like random forest, XGBoost, those kind of decision tree models, which are very apt for a fraud detection case. And you can, so yeah, in terms of a quantum machine learning, I have, so for example, this particular paper, which is very recently published by IBM, it's mixed quantum classical method for fraud detection with quantum feature selection. They are essentially using uh, the quantum version of support vector machines to come up with the optimal features for fraud detection. And I mean, if you're interested, this paper is classic. You should definitely go through it. But in general, for let's say this fraud detection problem is a classification problem essentially. So you either want to identify if a given instance is a fraud or it's not a fraud. And in quantum machine learning, so when we discussed about QAOA or VQE before, we did not talk about this thing called feature map. So this is essentially more common in quantum machine learning, where you have your classical data which you need to map to in a quantum way. So you have circuits which help you map your classical data to quantum, and you have the popular ones are these Z feature maps, ZZ feature maps. For reference, I have actually also put in these uh, snapshots from my Jupyter where you can see the circuit that you get from Z feature map, ZZ feature map, and you can always so yeah, the Qiskit documentation. If you look at it, it also has the paper link which have described these feature maps. They're pretty intuitive and simple to understand. Uh, Once you have that, and then you have once you have transformed your classical data to quantum, you again have the similar kind of a setup where you have your uh, ANSADs or a variational circuit. So you have that, and you have a classical optimizer. And the idea is that you keep running it for several iterations, like how you run in a neural network, you run, say, epochs. So you have several iterations that you run here so that you ultimately come up with a optimal minimum, a global minimum value. And value here, by the way, means that you find. So yeah, one thing is, so when we spoke about uh, variational quantum eigensolver, what does it mean to get a minimum of a Hamiltonian? Is essentially to get the energy value with respect to the ground state. The eigens value of the ground state is what we want. So essentially, you have this kind of measurement. One way of measuring it is basically to do something like uh, this that I have written here, something like a state uh, h x. Like you basically have that kind of a. So that basically that formula is basically used to compute energies, and you do that several times in several shots. So for example, even when you're iterating several times, every time you would essentially be uh, measuring the energy value and trying to get an average of your energy state. So what you end up getting is ultimately an approximation to your uh, energy value with respect to your ground state. Again, if this is, feel free to go over. In this summer school in 2022 had a lot about quantum variational quantum eigensolvers. So once it's released publicly, I'm sure you could go through it to even understand how it's analogous to this state, how you could use it for finance and other applications. Lastly, yeah, I mean, I have linked the Qiskit Finance uh, GitHub link here, which you should definitely go through if yeah. I mean, yeah, that's probably the end of it. Uh, yeah, I really hope this was good. I hope this makes you motivated to actually learn more about quantum finance.
Yeah, thank you so much.
Yeah,
That's really insightful into some of the areas that people can take quantum computing towards
yeah.
finance.
Yes.
Does anyone have any questions?
Uh, I think there is one chat. I have to. Okay.
I think that was a clapping emoji.
Yeah. Thanks. Yeah.
Okay.
Yeah, thanks for having me here. This, uh, yeah, yeah, definitely do stay in touch. Yeah, really thanks.
Yeah, thanks a lot. And if you could send me this slideshow afterwards so I can
Yeah, sure.
uh
Yeah, yeah,
give
definitely.
everybody the links that you mentioned in certain slides, that would be awesome.
Cool. Yeah, sure. Yeah, definitely. I'll share it with
Okay, well, thank you so much then.
you. Yeah, yeah. Thanks for having me. Yeah, it's great.
Yeah, of
Feels good. Yeah,
course. All right,
cool.
bye.
Bye.